Good morning. We are Team Cartographer, a group of 6 passionate individuals eager to present our innovative solution for the NASA App Development Challenge.
As a team, we work tirelessly to develop an app that meets all the expectations with user-friendly features. In the following segment, we'll display all the different features of our app. So, let's dive into the fascinating world of the lunar South Pole.
Upon opening our app, the user is prompted with the option to either load an existing site or create a new site. Upon the successful completion of the creation of a new site or the loading of an existing site, the user is presented with the credits page and the main menu. When the main menu is clicked, a new set of options to pick a landing site, rerun the pathfinding algorithm, or load a new site button, and sliders to adjust the volume of the music and controller sensitivity appear. In the upper left-hand corner of the app, we feature latitude, longitude, height, slope, azimuth, and elevation data. Adjacent to the data is a 2D minimap that displays the user's position as a mobile red dot. Below the minimap is the user's position in Cartesian coordinates for convenience.
3D rendering is done via a height map image that assigns color values on a black and white scale to corresponding heights. This is read by Ursina, our game engine, and generates the terrain.
The user is easily able to toggle between the regular texture of the moon, a slope map, a height map, and a path map using number keys 1 through 4 on the keyboard. Our standard texture generation is done via a bell curve probability based on an initial RGB value, which is then iterated through a number of times proportional to the slope at each location. The resulting RGB value is then drawn to the image to create a non-uniform texture with just enough randomness to be realistic and variable. Our slope maps and height maps are created through a Python library called Seaborn, which is commonly used for statistical plotting.
Our implementation of save functionality allows us to toggle between multiple sites in just one installation of the app. The UI, built with a Python library named PySimpleGUI, gives the user buttons to either input data files for each site or load an existing save in between runs, and uses system arguments to run a display script with different respective sites.
To pick a landing site, we used research from Holly Brown from the School of Earth and Space Exploration at Arizona State University. Her study compiled information regarding the presence of water and other volatile molecules from 10 remotely sensed datasets in 65 permanently shadowed regions, or PSRs, to estimate the locations and mass of water ice deposits measured by the Lunar Reconnaissance Orbiter. Brown's research concluded that the Gerlach Crater Rim 1 is the most promising landing site because of its access to 2 PSRs and solar resources, prevalence of viable communication checkpoints, and modest slopes traversing from illuminated terrain to water ice deposits.
For our pathfinding, we opted for the A-star algorithm. It's similar to the Dijkstra algorithm, however it prioritizes searching points that are closer to the goal before weighing points that are farther away.
Our app needed a better algorithm for calculating communication checkpoints. Our original algorithm was inefficient and only used elevation angles to Earth, creating some inaccuracies. After gaining some insight from a professor of astrophysics at UCI, we learned to use a pyramid-based search algorithm to determine if a node is a viable communication checkpoint. The algorithm scans squares expanding further and further from the original checkpoint to find a point that is not obstructed from communicating with the Earth.
We included a visual of Earth in the background to number 1, provide a realistic experience for the user, and number 2, to illustrate the basis of a valid communication checkpoint that is in line of sight of the Earth.
One of the main problems we ran into was an inefficiency in some of our code. One of the aspects of this was with our pathfinding algorithm. We attempted to use quad trees and spatial hashing to optimize our processes, however, they somehow ended up being less efficient than base A-star. Because of how A-star works by finding nodes that are closer before looking at nodes that are farther away, it turned out that adding quad tree optimization requires us to add every single node into a quad tree, and with a lot of nodes that actually hurt our efficiency more than just using base A-star. To also help with our optimization, we implemented JSON reading over .env or .csv. We also focused on NumPy optimization over for loops and switched to new, more efficient libraries instead of some hard-coded functions.
The problem with Python is that it's dynamically typed, meaning that variable types are determined when you run rather than when the code compiles. This means that it slows the code down. Additionally, it makes it harder to read for viewers and requires us to add extensive type conversions from floats back to integers and so forth. We fixed this by adding type hinting wherever possible to improve readability and speed.
As we ran many tests, we realized that we were spending more time waiting rather than coding. To fix this, we switched many of the for loops in our code to NumPy arrays to speed up the programs. Additionally, we added multi-threading to our image generation and data processing to run multiple tasks at the same time, making everything more efficient.
We brainstormed together to complete all technical suggestions that were given to us, such as adding key units for key data, rounding off any values, and adding a color key. We also followed the suggestions for more explicit changes like showing our path optimization, which focuses on lower slopes and the shortest distance between the user customizable landing site and destination location, while the checkpoints focus on visibility to Earth using an algorithm that projects rays from a point to Earth, checking for obstructions between the two. A-star is then reran between each chosen checkpoint by subdividing an original path into tenths, allowing us to optimize those paths for slopes and distance as well. We also included a visual of Earth in the background with the poles flipped for accuracy. To fulfill these suggestions, we learned a lot about the intricacies of A-star and heuristic equations, shader functionalities, in-game engines, and proper UI design.
While presenting to our local communities, we paid careful attention to present World Quantum Day, the initiative among educators and experts to promote understanding of quantum science and the latest technology. We also presented and completed Quantime activities to help consolidate this understanding for our audience. We also emphasized the benefits of quantum communication, which, by utilizing the properties of entanglement and superposition, can transfer information from one particle to another over a theoretically infinite distance. This enables quantum communication to overcome the issues of physical distance and barriers, which often acts as a limitation on classical communication.
We wanted to thank you, the SCaN team, for giving us this wonderful challenge in which we learned a lot and really became close friends. We had a lot of fun while doing it.
Thank you for your time.
Hello, this is the last week of the NASA App Development Challenge and we are pretty much done with everything now. I joined the team very late, but still it was a very unique and great experience for me. I learned a lot of new things, improved my skills, and most importantly, met with 5 amazing people. The fact that this is the last week makes me very sad because I will miss Abhi's director skills, Jaya's endless explanation of the A-star algorithm, Kabir's quantum presentation, Kion's GitHub contributions, and Nadalia's rehearsals. So before I finish my words here, I want to thank all of them for everything they did and having me in the team. I love you all. Thank you. Cut.